Now, we want to see how much is the improvement. But yeah, so here, from the formula point of view, we can compare the difference. Yeah. So, yeah, actually, I can show you the, the formula. Yeah. First, yeah, so Horner's rule, this is what we get for the Horner's rule. If we use the brute force method, we need this many multiplication. If we use Horner's rule, we need this many multiplication. So that's the improvement. Okay, that's the improvement. Yeah. All right. Yeah. So now we want to see the impact of multiplication in reduction. Yeah. How much is the difference? Yeah. In this topic, I want to give you some visual impression. Yeah. So let you feel about it. Yeah. Here, if you look at the formula, oh, sorry, I need to, yeah, because the light, yeah, looks better. Yeah. All right. Too abstract. Yeah, you look at the formulas, so you can see the difference, but how large is the difference? You cannot feel about it, right? You cannot feel how much is the difference. So now we want to feel about it. Yeah. Get some concrete feeling about the difference, the huge difference. Yeah. So let us work on some concrete examples to see the difference. Yeah. The first example, yeah, let us try n equals 1,000. How much is the improvement? Yeah. Here, we only look at the multiplication part. Yeah. Because addition part very tiny, right? Yeah. Very small little, we can almost ignore the addition part. Yeah. Yeah. So here, for simplicity, I want to ignore the addition part. Yeah. So you may ask, how can you ignore? Yeah. Because your estimate may not be very accurate, right? If you want to ignore addition part, may not be accurate. Yeah.
Even though the multiplication part,
oh, sorry?
Even though the multiplication operation is what takes up the most time as far as
yes.
the addition still constitutes a part of the overall running time. So you
right.
have to find a way to mathematically factor that into your overall efficiency analysis.
Right. But so here I want to do, so here for simplicity I only compare multiplication part because the percentage of the addition part is so tiny. So tiny. Yeah. Think about, yeah, so in our computer science, many times we need to do approximation. We need to skip minor terms. In our module 2, we will do this kind of things a lot. Minor terms, all right? Yeah. So here, think about, based on your real world experience. Sometimes you ignore some little tiny things, right? Yeah, everyone. Think about, if the part you want to ignore is only, accounts for 1% of the whole thing, do you feel comfortable to ignore it? 1%. If you ignore it, you lose 1%. Do you feel okay? So we can ignore it. How about 0.1%? Do you feel more comfortable? 0.1%.
If that's all the time that it takes, then it becomes more negligible.
Yeah. Or even smaller than that. 0.0001. Do you still feel okay to ignore it? Yeah, many zeros %. Later you will see the addition part. Yeah. So if you use that part, compare with the, total execution time, that could be 0.0001%. So don't worry, ignore it. Okay? Yeah. All right. So then, now we only compare the multiplication part. When n equals 1,000, let's look at, when we use the brute force method, how many multiplications do we use? Yeah. All right? Yeah. So here, if we use the Horner's rule, so here, Horner's rule, simple, 1,000 multiplication. the same number, this is the degree number, right? Polynomial degree. Yeah. So the number of multiplications, that number equals the degree number of your polynomial. Horner's rule. For the brute force, you plug in n equals 1,000 approximately. So here I use approximation here. See? I use approximation. Right? For simplicity. Okay? Yeah. Good enough. Yeah. 500,000, right? You plug in n equals 1,000. 500,000. Approximately. Not exact number, but very close. Okay. Let's look at the ratio this time. The difference, the ratio of the execution times for these two methods, 500 to 1. Is the improvement big? 500 to 1 ratio. Is that big? Yeah. So if you look at the 1, how much percent of the 500? 0.2%, right? Is it 0.2%? See? 0.2%. Yeah. So if the original execution time is this much, then for the brute force method, then after you apply the Horner's rule on the same polynomial, the new execution time only 0.2% of the original execution time. Is that big?
So you're explaining or implying the Horner's rule in this process?
Yeah.
And the Horner's rule, the way to apply that rule is to take like an input size and
Yeah.
size of the input
Right.
and
Same polynomial. We do not change the data. Okay? We apply two methods on the same set of data. That's the huge difference. 0.2%. That's small percentage. How big is the improvement? So that's the you know, at the beginning I said, let you feel about it, right? Now you can feel. Oh, only 0.2%. So I can feel. I know how much it is, right? Yeah. But this is our first example. I want to show you second example. Yeah. Because currently we are in a kind of big data era, right? So we are in a big data era. So sometimes we need to process large amount of data. Okay? Yeah. So the data size could be huge. Okay? That could happen, right? So think about if our data size becomes this big, n equals 1 million this time. Okay? 1 million. Yeah? So if our data size 1 million, this big, okay? Then let's do comparison. Okay? Yeah. Now, if we apply the Horner's rule, we need a 1 million multiplication. Same number. But now let's look at the brute force method. How many multiplications do we need? Let us plug in 1 million into the brute force formula. How large is this? Can you tell me the number? How large is this number? How do you call this number? How large? That many zeros. Look at number of zeros. 500 billion, right? Yeah. 500 billion, yeah, because 90, that's the billion, okay? Yeah, 90, that's the, billion. 500 billion. Yeah. Take the ratio, 500 billion over 1 million. What's the ratio? 500,000 to 1. That's the ratio, 500,000 to 1 ratio. Look at the huge difference. In this situation, look at the huge difference. Okay? Yeah. If you apply the brute force method, you need certain amount of time, let's assume, certain amount of time. Now, next, you switch to Horner's rule. You just need 500 thousandths, right? 1 over 500 thousandths, right? Yeah, 1 over 500,000. That little tiny amount of time, you can complete it. That's huge, right? That's huge. Yeah. So to let you feel about this huge difference little better, in a little better way, I like to use, another way. Suppose this 1, yeah, because this 1, we know, 1. How large is this 1? Let us interpret that 1 as 1 second. How about that? 1 second, okay? Yeah. You know how long is 1 second, right? Yeah. So in your mind, you know how long is 1 second. Okay, all right. That 500,000 seconds. If you use the brute force method, you need 500,000 seconds, right? Yeah. How long is 500,000 seconds? Yeah. Yeah.
Probably even more than like a day.
Yeah. So we want to see how many days, okay? How many days, hours, minutes, that kind of thing. Let's do the conversion. Okay, we can do the conversion. Yeah. 5.8 days. If you do conversion, so divided by 60, another 60, then 24, in that way, you need 5.8 days. Is that huge? 5.8 days versus 1 second. Okay? If you apply the brute force method on this 1 million degree polynomial, you need 5.8 days to get an answer. Okay? After you hit enter, then you can go to vacation. Okay? After 5.8 days, after you come back, you see the answer. All right? But if you apply Horner's rule, after you hit enter, after 1 second, you see the answer, the same answer. Is that a big difference? Yeah? So now you see the power of the efficient algorithms. I use this example to show the huge difference about efficient algorithms. Yeah. So for this class, why we need to take this class? Okay? Other than the degree requirements, we need to learn problem solving. We want to find efficient solutions. We don't want to find slow solutions. So how efficient? Here you can see the impact of efficient solutions. 5.8 days versus 1 second. That's the big difference of two different algorithms. Okay? Yeah, so that's your first programming project. Okay? Brute force, you need to implement brute force. Then Horner's rule, the third one. Yeah. Then there is the second one. So next I will talk about the second algorithm you need to implement in your first project. All right. Yeah. So B.5, repeated squaring technique. Actually, we did it. Yeah. Remember, somewhere in the middle, yeah, we calculate x to the 4th with 2 multiplications, right? Yeah. At that time, we did multiplication. We do square operation twice, right? We do square operation twice. So that's actually this method, repeated squaring technique. We'll keep doing square operations many, many times to save number of multiplications. This is our second algorithm in our programming project. Okay? Yeah. 1, 2, 3. 1, brute force. Number 2, repeated squaring. Number 3, Horner's rule. Okay? Yeah. All right, so let me explain this repeated squaring technique. Yeah. This time, when we apply, we work on the monomial, one term, okay? Not polynomial directly. Yeah. We need to use the minimum number of multiplications to calculate monomial. All right, that's how to find an efficient way to calculate its value. Yeah. So this question. Yeah. All right. Yeah. So here, also give the reference section 6.5. Yeah. All right. So what do we have so far? Yeah. Yeah. Although we can apply Horner's rule, yeah, but in this is a special case. In this special case, the Horner's rule does not help much. The Horner's rule does not help much. Yeah. What's the reason? The reason is simple, because why Horner's rule can reduce the number of multiplications by factorization, right? Now you have single term. You have no place to do factorization, right? Yeah, factorization, doesn't help here, okay? Doesn't help. So that's why if you apply Horner's rule here, doesn't help. Yeah, for this special case. Yeah, all right. Yeah, yeah. So, yeah, but the power of the Horner's rule is on the general polynomial. Yeah, may not be on special polynomial. Special polynomial Horner's rule may not be the best way. Yeah. General, yeah. General. That's the best we can get so far. Yeah. Probably people believe it's the best method for the general polynomial. Yeah. All right. How about the special case? Now we need to look at some special cases. Yeah. All right. So let's consider the special case. Yeah. Let's look at our first special case. Yeah. Yeah. So we already have the answer for this case, 2 multiplications. We did before. Yeah. Now, so to do it, we do square operations twice. We skip x cubed step to save 1 multiplication. Yeah. In this case, we do not calculate x to the 4th, x to the 3rd. So you can save 1 multiplication. Yeah. All right. Yeah. But now let's consider the general case. A little more general case. Yeah, not the completely general. When n is the power of 2. N equals 2 to the k. 2 to the k. Yeah. Power of 2. Yeah. This time you can see how many multiplications do we need? 2 to the k. By repeated squaring. Yeah. All right? Yeah. So here, let's do experiment. Yeah. Yeah. All right. Do the chart. First column, the k number. Second column, the monomial we want to calculate. All right. Then third column, we want to count the number of multiplications we need. Yeah. All right. When k equals 1, then we do calculate x squared. X squared, 1 multiplication, right? Yeah. K equals 2, x to the 4th, we did it before, 2 multiplications. Okay? Yeah. All right. K equals 3, x to the 8th, how many multiplications do we need? How many? 4? Think about it. Yeah, here, let me give you some hint. After 2 multiplication, 2, here it's 2, you already have x to the 4th. Yeah, 3rd. Because you can use x to the 4th, you just need another square operation, right? Yeah, another square operation. So, 3 multiplications. Yeah, 3 multiplications. Can you see the rule? Yeah, after these 3 experiments, can you see the rule? Yeah. Do you have enough information to tell you when you have a general K. K is a general K number. Yeah, now you need to calculate x to the 2 to the K, this number, how many multiplications? Based on the experiment data, you can observe some rule. Any conclusion you can give me? K, exactly. K. We apply induction here. Yeah. This is, we call it induction. Okay? Induction. Answer is K. Answer is K. All right. Then, is this a big improvement? Think about how, if we can apply repeated squaring technique, is it some big improvement? Yeah, let me show you one example to see how big is the improvement. All right. This time I take K equals 10. K equals 10. Then N equals 2 to the 10, that's 1024. Now we need to calculate this monomial, x to the 1024. Okay? Yeah. By repeated squaring, we need to do square operations 10 times, right? 10 times. Square, 10 times. 10 multiplication, right? 10 multiplications. Yeah. That's the improvement. Yeah. Yeah. Now you tell me, if we do not apply repeat squaring, if we just apply brute force method to calculate x to the 1024, how many multiplications do we need? Brute force. How many? 23. 1023. One fewer than the number you said, degree number. Why 24? Remember, we need to multiply some A coefficient, right? 1024, that number comes from, you have some certain coefficient number, right? Leading coefficient, A something, A sub 1024. But here, our leading coefficient is 1. Then you don't need that multiplication, right? You don't need that last multiplication. That tells us, by brute force method, we need 1023. Now you do comparison. How big is the improvement? 1023 versus 10 multiplications. 10. Huge improvement, right? Yeah. Huge improvement. Yeah. Because if you skip the major part, 1000, you have 23, more than double of that 10, right? Yeah. See? The saving is huge. See? So repeated squaring, but only when you calculate monomial, this is the best way. Calculate the monomial. Yeah. Yeah. Oh, to be precisely, this is the near best. I should not say the best, because there is a special case. This may not be the best. Yeah. Close to the best. Yeah. Not always the best. Sometimes best. Sometimes close to the best. Yeah. That question I will answer later. Yeah. All right. Yeah. So here I show you the power of this repeated squaring technique. Yeah. The essence of the method. Yeah. Here I give you an important idea in problem solving, in the real world problem. There is a very important idea. Look at this. Essence of the smell. Why the improvement is so big? Yeah. We need to understand the reason. Yeah. So we need to learn from this big improvement. Reuse the resource as much as we can to save operations. This is a general idea. Reuse the resource. What's the meaning? Reuse the resource. Yeah. When you have certain resource, I will explain the resource later. When you have certain resource, we know our resource very precious, because we spend a lot of money to build up our resource. After you spend a lot of money, you don't want to waste it, right? So you want to use your resource as much as you can, right? Yeah, to get some benefit. Yeah. So here's the idea. Very simple, right? Reuse your resource as much as you can. Yeah. Now, let me explain this resource. In our computer's algorithm context, this meaning of the resource is intermediate computation results. That's our resource. Intermediate computation results. When you need to calculate some specific result, yeah, so your destination result, you need to calculate a lot of intermediate results, right? Yeah, to do preparation for the final result, yeah, intermediate results. But all the intermediate results, that's your resource. Because that kind of resource is reusable. You can use, well, that's all the resource in your pocket. You own that resource in your pocket. So you can use it directly, right? Yeah, because you have it. Anytime you need, you use it directly. You do not need to rebuild, right? If you rebuild, you need more time. You need to, more resource to rebuild, right? Yeah. Yeah. Save your other resource to rebuild. Just use directly. All right. Now, use this understanding. Let us look at repeated squaring. How do we reuse the resource? Our goal, we want to calculate x to the 2 to the k, that monomial. Now, the first time we calculate x squared, then this becomes our resource, right? Yeah. So you hold it, yeah. You store it, do not throw away, okay? Store this x squared, intermediate result. Do not throw away, that's your resource. Next step, when you calculate x to the 4th, you reuse x squared, right? You use it, okay? So you grab it from your pocket, then you use the x squared directly, so you can get x to the 4th immediately, right? Then next time, when you need to calculate x to the 8th, this time x to the 4th is your resource in your pocket, okay? You can use it directly, so you take it out and use that x to the 4th, then you can get x to the 8th very fast. So you keep doing this, okay? Every time reuse your resource, yeah, to get a new intermediate result, step by step. At the end, you get the final result. Through this we use this idea. Okay? Reuse the resource idea. Okay? All right. Yeah. Yeah. And this idea is very general. General, that means when you work on other computing problems, yeah, yeah, so you can, many cases, you can use this idea. Okay? Reuse the resource. Yeah. This idea. Okay? Do not throw away your intermediate results. Store somewhere. Okay? We know in modern computer, the storage cost very little, right? Storage cost very little, okay? Yeah. But you can save a lot of time. You use a little storage cost. Yeah. So you're willing to pay, yeah. But the gain is huge. The gain is, you save a lot of time. That's the gain. Yeah.
That's the magic of efficiency.
Yes.
Using algorithms that
Yes.
are specifically designed to max out efficiency.
Yes, yes. At least, yeah. At least this is important.
And this is not Horner's method, right? Because this is not.
Yeah, not Horner's
It's
method.
not standard polynomials.
Right.
So what would be the name of this method?
Repeated squaring. Okay? Yeah, yeah. Repeated squaring technique. Yeah. All right? Yeah. 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 All right. Yeah. So I finished. Now I finished explain this whole algorithm. Yeah. Now, but I haven't completed. Yeah, because here we only consider n equals power of 2, right? Yeah. We only consider n equals power of 2. Yeah. So we need to consider the general case. If n is not power of 2, then we want to generalize this repeated squaring technique. Yeah. All right. Yeah. Not power of 2. Yeah. So here, let's try example. N equals 217. Not power of 2. Yeah. But we can still apply the idea, reuse the resource. Right? Reuse the resource. We can still use our stored resource to calculate this monomial. Yeah. All right, let me show you. What is the largest? Yeah. So first, we can do preparation in order to calculate this monomial, x to the n, this n. We need to do some preparation. Yeah. So the preparation is, I want to look at what is the largest power of 2 under n, smaller, yeah. Under n. Yeah. Let's look at that. Yeah. Yeah. So we can see 128 equals 2 to the 7th. That is less than or equal to this number, 217. But if you calculate 2 to the 8th, then it is larger than 217. 2 to the 8th equals 256, greater than 217. So we cannot use it. Yeah. So we need to use the power of 2 less than or equal to 217. Yeah. Next, we want to calculate what is the fastest way to get x to the 128th, that monomial. Fastest way. Repeated squaring, right? That's the fastest way. Repeated squaring. Yeah, all right. Yeah. We need 7 multiplications. Yeah. Because 2 to the 7th, right? That exponent number is the number of multiplications we need using this technique. Yeah. Exponent number, 7. Yeah. All right. Now, we need to reuse the resource, this idea. Let's collect all our intermediate results. Yeah. Because when we calculate this number, x to the 128th, we need to prepare some intermediate results, right? Yeah. Let's collect them. Yeah. Let's do not throw them away. Yeah. Store somewhere, collect them. So all these monomials, all these our resource, intermediate results. Okay? Intermediate results. So we store all these numbers ready for calculation of our final monomial. Okay? Final monomial. That's our destination monomial. We need to calculate. All right? Yeah. Then let's do the calculation. We do decomposition. We decompose this number, 2 to the 17, as sum of power of 2. Yeah. If you can represent 217 as sum of power of 2, can you use your resource to do the calculation? Right? You can use the resource to do the calculation. All right? Let's do the first step, decomposition. Power of 2, remainder 89. 89 is not power of 2. Let's write 89 as sum of other power of 2 numbers. Okay? Another level. 64 is power of 2. Okay? Yeah. Then remainder is 25. Next step, we need to represent 25 as sum of power of 2. Okay? Yeah. Next, 16. After 16, then 8 power of 2. The last power of 2, 1. Right? Yeah? So this is the decomposition of power of 2 decomposition of the original number. Okay? Yeah. All right. After we have this decomposition, then we can represent our target monomial as a product of our resource numbers, right? Resource numbers, yeah. X to the 28th, we can copy from our pool, resource pool, okay? X to the 64th, resource pool, copy, all right? And so on. All the numbers you can get directly. Yeah. But at the end, you need a few more multiplications, right? See, each dot is one multiplication. 1, 2, 3, 4, right? 1, 2, 3. You need 4 more multiplications to get your target monomial. The target monomial, okay? Let's count the total number of multiplications. 7 plus 4, 11. 11 multiplications. We can find x to the 217th monomial. So for a general number, you use this way. Yeah. But another view, because we need to look at the view. Another view, when you look at the power of 2 decomposition, that actually corresponds to binary representation of this number, right? Yeah. Binary representation. We know this is a decimal number, any decimal number you can convert it to the binary representation, right? Yeah. If you convert it to binary representation, then it corresponds to the decomposition of power of 2. See? Yeah. All right. X to the 7. Yeah. All right. Here, let me suppose we use 8 positions. I use this 8 positions. Okay. All right. 1 corresponds to 2 to the 0, So the first bit I change to 1. X, 2 to the 3rd, 8, right? 2 to the 3rd. So, 2 to the 1st, 2nd, 3rd, 2 to the 3rd. Oh, sorry. Oh, what's wrong? Which is the right one? Anyone? Yeah, let me see. I couldn't find it. No, this one. Anyway, yeah. Too sensitive. Yeah. Right here. All right. All right. Yeah. All right. So here. All right. 1, 2, 3. All right. 2 to the 3rd. I change this to 1. Okay. 16. I change this to 1. 2 to the 4th. Then I skip 2 to the 16, 64, 2 to the 6th, I change this to 1. And the last one, change this to 1. Okay? This is the binary representation. Yeah. All right? Yeah? So corresponding to all these power of 2. If you can write binary representation, then you can write decomposition of power of 2. Okay? Then you can calculate that. All right? Yeah? That kind of relationship. All right. So then, so here, when you work on the general case, we just prepare our resource pool. This is our resource pool. Okay? Yeah. For appropriate K. Yeah. So what's the K? Yeah. K, that is the largest power of 2 less than or equal to n. Less than or equal to n. So then you use that K, you prepare your resource, okay? Intermediate results. Yeah. Then you write a decomposition like this. Then you do the calculation, okay? All right, yeah. So here, so you right. That, yeah. So in this way, so you, right. In that way, you can calculate the general N. Okay, yeah. All right. All right. Yeah. This is our algorithm number 2 in our first programming project. Yeah, first programming project. Okay? Yeah. Then, when you calculate each monomial, you use this method. Okay? Each monomial. But after you get a monomial, then you need to add up all the terms. Yeah. But you do not do factorization. Okay? Yeah. You do not do factorization. Yeah. So when you use this method, it should be slower than Horner's law. Slower than Horner's law. So you will see this method. Yeah. Our second algorithm based on repeat squaring will be, for the general case, slower than Horner's law. Horner's law is the fastest. Okay? So, but faster, much faster than brute force. Yeah. Brute force is the slowest. Then repeated squaring.
So this is a repeated squaring method too, right?
Yes. Yeah. But to write the repeat squaring code, yeah. So I'll give you the pseudocode. Yeah. The pseudocode, yeah, for this repeated squaring method, we can use recursion. Okay. Yeah. Here we can use recursion to implement this repeated squaring. Yeah. Otherwise, if you do not use recursion, still you can do it. Yeah. Without repeat squaring, you need to write a binary representation first. Then, based on the binary representation, you use a for loop. Yeah, no problem. We can do that way. But more complicated than recursion way. Recursion way much simpler. Okay? Yeah. So based on our textbook, section 6.5, you can use this recursion method. Recursion method. All right? So let me show you the recursion method. Yeah. The base case, when n equals 0, you do not need to do calculation, right? Yeah. That's 1. You return the monomial, that monomial 1 value is 1. If n equals 1, yeah, return x. Yeah. Yeah. These are 2 base cases. Other than these 2 base cases, now we need to look at the general case. For the general case, we need to, so here, we do integer division by 2. N over 2, that's integer division, right? So integer division, you truncate the fraction, no part. Yeah. So you do truncation. You only keep the integer. Then, recursive call. Yeah. The same function, x, but with the degree n divided by 2, integer division. Yeah. Integer division. Yeah. All right. Then, for n even odd, this integer division has different results. Yeah. All right, so now we need to, let's calculate the first intermediate result, this result variable. We store the intermediate result. Intermediate equals this product variable times square. This is square operation, right? Yeah, so you recursive call, you do product times product. Yeah, you get this intermediate result. Yeah. Then, next, we need to consider even odd, and even and odd 2 cases. N mod 2 equals 1. That means odd case, right? Odd case. Remainder 1. When you do n mod 2, remainder 1. That's odd number. If it's odd number, then you need to do one more multiplication. Result. Modify your intermediate result. Result equals x times its previous number. Okay? Yeah, because odd, you have truncation here. You need to make up that truncated part, right? Yeah, because you cut off one x operand. So here, you bring that cut off x operand back. So you need to do one more multiplication, x times product, right? But The other case, m mod 2 equals 0, you do nothing, right? Yeah, because no truncation. That means no truncation. No truncation, this previous result number is the final number. You can use it as the final number. You don't need to do modification. Yeah. All right. Return this after this, 50% of the cases, you do modification. Yeah. You return this result. Yeah. That's the pseudocode. Okay. Yeah. Use recursion. Very simple. Very simple. Yeah. But you can use that binary representation. Then you do not use recursion. You use for loop. Yeah. Based on the binary representation, for loop. Okay? Yeah. In our module 3, we will compare the difference of these two methods: recursive method and iterative method. For loop based, that's the iterative method. Yeah. Recursion based, yeah, this method, recursion method. In our module 3, I will compare these two methods. Yeah. All right. Yeah. So we finish this topic. Yeah. Yeah. I do not have much time, but yeah, to help you answer quiz question number 10. After you get a repeat squaring, you do not have enough knowledge. So we need another topic to get you ready for our last. Yeah, that question very challenging, very, very challenging. So I need to give you another block of knowledge. Yeah. Let me get out of this topic because I need to skip one topic. Yeah. One topic here. Yeah. That topic called repeated cubing. So later sometime I will come back because for your quiz you don't need this method. Okay. So I just skip this one. Later, after we complete part D, then I come back. Okay? Yeah. All right. Yeah. Then, this B.7, you need this knowledge for quiz 10. Yeah. So let me talk about it. Yeah. Yeah. Before we, finish today. Yeah. So you can come do all the questions of your quiz 1. Take advantage of the structure of Pascal's triangle. That's the title. So here, let me talk about why we need to use another block of knowledge to answer quiz 10. Quiz 10, if you read the question carefully, yeah, read the question carefully, because quiz, that question, we do not work on monomial, right? Yeah. Repeat squaring, that works on monomial. If it's not monomial, then you cannot use repeated squaring. Yeah, but that question, you consider a polynomial with n terms. Polynomial with n terms, that's not monomial, right? So you cannot apply repeated squaring directly. Yeah. But you can use indirectly. Not directly, but indirectly. How indirectly? Use this topic. You can do one transformation. You need one transformation, then you can apply repeated squaring. If you do not do transformation, then you cannot apply repeated squaring. Okay? So here I talk about that transformation. All right. Yeah. So what's that? Yeah. All right. Yeah. So this topic, only one slide. Yeah, one slide. I try to complete before the end of the class. Oh, I cannot leave this computer very far, yeah, because Zoom side, they cannot hear if I leave. All right. Anyone knows this Pascal triangle?
Oh,
yeah. Yeah.
Pre-calculus.
Yeah. Whatever. Yeah. Yeah. So something interesting. Yeah. So you start from top 1. Next row. Yeah. Two numbers. Yeah. Use the shoulder number. But the next row here. Yeah. This 2 equals the sum of two numbers on its shoulder. Okay, 2. Okay, right? Yeah. Yeah. 1 plus 1. Then this 3, 1 plus 2. This 3, 2 plus 1. Okay? This 4, 1 plus 3, 3 plus 3, yeah. So you always use this way to generate the numbers in the next row. Then we call this Pascal triangle. Yeah. Why it's interesting? Because it corresponds to binomial formula, binomial expansion. Yeah. In discrete math, you have binomial formula, expansion formula. Binomial expansion formula, yeah, let me explain that binomial expansion formula a little bit. All right? Yeah, this is binomial, okay? X plus y to the nth, binomial. Yeah, 2 terms inside the parentheses. Yeah, but there is a formula. People also call it Newton's formula. Newton discovered this formula, Newton's formula. Yeah. All right. When we write the expansion, we need to use combinatorial numbers. Yeah. You know the combinatorial numbers? Yeah. Recall a little. Yeah. In discrete math, you learn the formula combinatorial numbers. I will give you a formula later. Okay. All right. So you use the combinatorial numbers as the coefficients to write the binomial expansion formula. Okay. All right. Here, let me give you the combinatorial number, the definition of this. N choose K. Yeah, we read in this way, the parentheses, top N, bottom K. People, read N choose K. N. We choose K from N. Yeah. There are N objects, but we need to choose K objects from N objects. How many ways to choose? That's the original meaning. The meaning of the, I cannot leave, yeah. The combinatorial number, okay? N choose K. Yeah, all right?
Ways to choose K numbers from instead of N numbers?
Objects, number of objects. N means N objects. You can N, balls, yeah, ping pong balls, things like that, objects. But you need to choose K objects from total N objects. How many different ways? The counting. Yeah. In your discrete math, you have that topic. Okay? All right. The final answer is N factorial over K factorial times parenthesis N minus K factorial. Okay? That's the formula. Oh, I need to look at the time. I may not have enough time. Then, now the first row in Pascal triangle corresponds to binomial x plus y parenthesis to the 0. Yeah, that's 1, right? The second row corresponds to x plus 1 to the first. Okay? Third row, x plus y parenthesis square, and so on. Okay? We keep doing that binomial, yeah, correspondence, yeah. And using this Pascal triangle rule, generating rule, you can get a corresponding combinatorial number coefficients. Okay? So that's the knowledge you need to use. Pascal's triangle. That's the knowledge you need to use. Okay? All right.
Can I take a picture?
Yeah, sure. Yeah. All right. I need to use the remaining 2 minutes to complete this whole thing. Okay? All right. So now, here, I'll give you a special example. Now we want to calculate. This is a polynomial, right? Yeah. But its coefficients very special. If you examine the coefficients of all the terms, it corresponds to this row, right? In the Pascal's triangle. See? Corresponds to this row in Pascal's triangle. Then you can apply binomial formula, right? Yeah. Binomial expansion. Yeah. Yeah. Because if you use the Horner's rule, based on Horner's rule, you need 4 multiplication, right? Because the leading coefficient is 1. So you can save 1 multiplication. 4 multiplications. Okay? All right. Then, now you use Pascal's triangle because it's a special polynomial. Yeah. You can take advantage of its special structure. Yeah. So by the binomial formula, you can write x plus 1 parenthesis to the 5th. Okay? Yeah. Then, is it just like a monomial? Yeah. The number is a addition because we we ignore the addition, right? Think about, yeah, addition, too little. So we don't worry about the addition, okay? So we can treat this as a one number. X plus 1 is a one number, okay? Then you calculate monomial. This time you can use repeated squaring, okay? So let us apply repeated squaring. The first square, x plus 1 times x plus 1, x plus 1 square, one multiplication, all right? Yeah. First multiplication. Second multiplication, another square, we get x plus 1 to the fourth. Yeah. X to the fourth, second multiplication, okay? All right. Then we need the last multiplication to get our destination formula. So total, we need 3. Look at from 4 to 3. Is that a big improvement? That's an improvement, right? We can do better. Yeah. Now you can connect to the question 10 of quiz 1. Question 10, because I tell you, n terms. Can you imagine the coefficients? You use the coefficients corresponding to some line, certain line in Pascal's triangle, okay? Pascal's triangle. Then you can use binomial formula to get a monomial representation. Then you can apply repeated squaring, right? So now you have enough knowledge to answer question 10 of quiz 1. Okay? Yeah. All right, that's it.